Now we are going to continue with our in-presence part of the session. And it is my pleasure to introduce you Cintia Pacchiano from the University of Calgary. She's going to talk about regularity results for double phase problems on metric measure spaces. Thank you, Cintia.
Okay. Okay. Thank you, Juan Carlos, for the introduction. Thank all of you who are currently here, and also the people on Zoom watching. And obviously, thanks to the organizers for such a lovely workshop. So yes, as the title of my talk says, today I'm going to talk about regularity results for the double phase problem. But the novelty here is that we're going to work on metric measure spaces. Now, before starting my talk, here is the outline. So I do want to start by talking a little bit about the connection between variational methods and just doing analysis on metric measure spaces. Afterwards, I am going to introduce our problem, so the double phase problem, give some motivation and background behind it. Then I'm going to define our setting. So what is it that we need to ask our space to be able to work in it? And also, obviously, what do we need to ask to be able to work in it, like to work with the problem that we're interested in, right? Then I'm going to state the main result. So mainly the gradient high integrability. And because of time restrictions and also because it can get quite technical, I'm not going to give any detailed proof, but I'm going to tell you guys the scheme of the proof. And at the end, if I have a little bit of time, I will talk of what has been done or can be done next. Okay, so let's get started. And motivated actually by a lecture course that I took a long time ago when I was a bachelor student here in Mexico, by Monica Clapp, I do want to give you guys a little bit of an introduction about variational methods. So this, with the purpose of to lead, what is the connection between calculus of variation and the actual like calculus on metric measure spaces? So many phenomena in nature, I mean, in physics or in, I don't know, biology, medicine, whatever, can be modeled via a partial differential equation. And many of these models actually have a variational formulation, meaning that the solutions of the model are actually the critical points of a certain functional that comes in the shape of an integral defining a certain function space. Now, this integral usually represents some sort of action or an energy or a cost function for those who do finite. But so for this model to actually make sense, the first thing that we need to ask is whether this model has a solution, right? Now, for many years, the model itself was kind of, how do you say this? Like every time we think of the model, we think of the phenomenon it describes. Now, in nature, it's very common to have an equilibrium potential. This is why, I mean, this fact was enough evidence for Gauss, for example, to say that then the variational integral must attain a minimum. But it was until the end, almost at the end of the 19th century, when Weierstrass here realized that there's an actual difference between reality and the model itself. And Weierstrass here actually gave us an example of an integral that does not attain its minimum. And this is very good because Weierstrass gave us the starting point for the methods of calculus of variation to start to develop. So the first main goal in calculus of variation is to prove that there is at least one solution to the variational problem, right? After we get this, well, it is also interesting to see how this solution behaves. What can we say about its regularity? How many solutions do we have? What type of stability, or if we have symmetries and so on, right? Like lots of questions. But let's focus now for a moment on this example. So the P-Dirichlet integral. And to make things easier, let's make P equal to 2. So basically, the associated Euler-Lagrange equation will be the Laplace equation. So let's focus for a moment on the Laplace equation, right? So we would be looking for functions whose Laplacian vanishes. Or let me say it in another way, we would be looking for harmonic functions, right? But this problem of looking for harmonic functions can be, it's a tricky one. It is very restrictive because it even depends on the domain we're in. So it was actually this need to look for harmonic functions that led Riemann here to think of this problem in a different way. Riemann was like, what if instead of looking at the PDE, we start studying the variational formulation? So Riemann actually was the one who gave us the Dirichlet principle. And this is fantastic for us because we realized, okay, so maybe we can obtain all these regularity theory for partial differential equations. I mean, not only regularity, also existence for partial differential equations without actually having to rely on the partial differential equation itself and just focusing on this variational integral and its properties. So one asked, okay, so can we obtain all these amazing partial differential equations theory in spaces where we don't necessarily have access to a differential structure as we know it? And this is where we come in, of course. So the main interest in my work, well, it's to extend some classical results of the calculus of variations to metric measure spaces. And I focus mainly on methods which in Euclidean spaces correspond to existence and regularity for nonlinear, parabolic, and elliptic partial differential equations. And just a very important example is the parabolic P Laplace equation, as well as just the elliptic one, right? Now, sometimes as mathematicians, we do need to stress like the relevance or why is it important what we do. And one of the advantages in working on metric measure spaces, well, it gives us a unifying framework, right? And it not only has applications within mathematics, also applications in other disciplines such as computer science. Obviously, because we will be working in a more abstract setting, this might give us new results, new even in a Euclidean case. And well, the last one, as I already mentioned, and this is maybe just for me, but the fact that we can have access to the theory, regularity theory of partial differential equations in this metric setting, that's what makes it interesting. Okay, so all these was like the brief introduction. I hope you understood the connection between variational methods, which is the thing that I enjoyed the most, and metric measure spaces. But we are interested in the double phase problem. Now, in the Euclidean case, the double phase problem and the double phase functional corresponds to the following. So it will be the integral over a certain open, usually bounded domain in Rn of the modulus of the gradient to the exponent p plus a coefficient function times the modulus of the gradient. Oh, here it should say q. I'm so sorry. It should say q. But okay. So this is the functional, and the basic assumptions or the standard assumptions are for both of the exponents to be bigger than 1, p less than q, and the coefficient function to be non-negative and being Holder continuous for an exponent between 0 and 1. Now, throughout this talk, just some notation, the functional over here will be denoted, it's usually denoted by h, and just to emphasize, the Euler-Lagrange equation associated to this integral is the following. Now, this problem is very interesting. And it's very interesting because precisely the coefficient function here. Now, we have like this functional, the behavior of this functional depends on this coefficient function. Notice that, well, we are assuming that A is non-negative. But precisely when A is 0, then this goes away. So we are left with basically the P Dirichlet integral. So P growth, okay? And when A is bigger than 0, when, well, we cannot get rid of anything, and we have a PQ Dirichlet integral. So basically, the ellipticity or the growth, it's determined by the 0 points of our coefficient function. And the main motivation behind why did we start studying this problem was because of a previous work that I did with Antonella Anastasi from University of Palermo. And in this work, we studied the PQ Dirichlet problem, and we were able to obtain higher integrability, stability, anything. But so the thing is that the PQ Dirichlet integral here, as you can see, we now are dealing with two coefficient functions, A and B. But these coefficient functions, we are going to assume that they are bounded away from 0 and infinity. And this problem in itself, it's already very interesting. It has, and I will need my sheet here, because so it has application or motivation from physics. So for instance, when we have like a composite material, any composite material can be described this way. So we have this composite material, and the coefficient functions A and B can dictate the geometry of the composite made by two different materials with the hardening exponents P and Q. But through working on this project, we were like, okay, so what happens precisely when we allow the coefficient function here that it's besides the term with the biggest exponent to be 0, which is precisely, I will do that, which is precisely, it's not working. Okay. Which is precisely the double phase, oops, what happened? Okay, yes. Which is precisely the double phase problem, right? So once we decided that we wanted to work with the double phase project, we focused on the work done by Colombo and Mignone in their article, and this article is the Euclidean case. And actually, in recent years, there has been a lot of work done for the double phase, specifically in the Euclidean case, and all this work has been done by this Italian school, so Colombo, Mignone, Baroni, Cristiana De Filippis, but for the purposes of this talk, we mainly gravitated in this work of 2015. A little bit of shameless self-promotion here. If someone is further interested, this talk is motivated by a recent work done with my former supervisor, Juha Kinnunen from Aalto University, as well as Antonella Anastasi from University of Palermo. The preprint is already available on archive and hopefully soon to appear in proceedings of the American Mathematical Society. But okay, so we now know that we want to work with a double phase. So what is it that we need to ask our space, right? So when working on metric measure spaces, one really has to focus on how to overcome just certain difficulties that will come from the fact that we are just working on a general setting. So we are going to start with X metric measure space. And the first thing that we are going to assume is that X is complete and endowed with a Borel measure mu. Once we have this Borel measure, hopefully now it works because I don't know what was happening. I cannot click on it. But okay, once we have this Borel measure, we're going to assume that the measure is doubling. What does this mean? That the measure of the ball, it's bounded by a constant times the measure of the ball. And this should hold for any point, any radius. Now, assuming that the measure is doubling, is somewhat standard in, for example, harmonic analysis, because it implies that the measure is finite dimensional. Okay, now, when working on metric measure spaces, we don't have access to the standard gradient as we know it, because there is no concept of direction. Therefore, partial derivatives, well, they have no meaning. This is why we work instead with what is called upper gradient. So a non-negative Borel measurable function g on x, it's going to be an upper gradient of u if for any rectifiable curve, the following inequality holds. Now, assume that we are in Rn. So we clearly have that the modulus of the gradient of u satisfies this inequality. So we can think of upper gradients as a generalization, but they will be a generalization of the modulus of the gradient. So unfortunately, on metric measure spaces, we lose the linearity that we had with the gradient in the Euclidean case. Okay, so one major drawback about this definition is that the integrability of the upper gradient is not controlled by the function itself, meaning that an upper gradient of u, and then we add any non-negative, just any non-negative constant, we get again an upper gradient of u. So we don't have uniqueness. But in order to counteract this drawback, we are going to work instead with what is called minimal p-weak upper gradient, minimality in the sense of the LP norm. And so now every time I say upper gradient, I'm going to actually refer to the minimal p-weak upper gradient, which is like a unique thing. Okay, so unfortunately that doesn't work, but so now we have a concept of gradient, right? So we can do as we do in the Euclidean case when we define Sobolev spaces, but this case we call them Newtonian spaces. And the construction is basically the same. So no need to linger on that. And since actually the construction is basically the same, in some literature, they are called Newtonian Sobolev spaces. And the notation now will be N1P instead of W, N1P. Okay. So we're headed in a very good direction because now we have function spaces. But at the end, we need a connection between the underlying measure and the upper gradient that we just defined. This is why we need to assume that our space supports a weak Poincaré inequality. And what I mean by that is that we say that X supports a weak QP Poincaré inequality if there is a constant and a dilation factor such that for any open ball, any integrable function, and any upper gradient, the following inequality holds. Now, two things about this inequality. The first thing, just notice that here we're working with the ball, and then here we're working with the dilation, okay? And the second thing is that indeed this inequality gives us a connection between the upper gradient and the underlying measure. So what this inequality is basically telling us is that if the upper gradient is small in average, well, then our function cannot oscillate too much. Okay, so those are the basic assumptions or the standard assumptions over our space. For X to be complete, endowed with a Borel double measure mu and supporting a weak 1p Poincaré inequality. Okay, but to refresh your memory, we want to work with the double phase problem, right? So we want to prove regularity properties and mainly higher durability for the upper gradient of quasi-minimizer for the following integral. And now notice that the notation changed, right? Like I already introduced you what the upper gradients are. So now this integral is in terms of these upper gradients, okay? And we're gonna work under standard assumptions, right? So again, Q and P are going to be bigger than 1 with P less than Q. And we are gonna ask for the exponents to be close together. And this closeness property, it's gonna be in terms of this alpha, which comes from A belonging to a holder, to being holder continuous for a certain alpha between 0 and 1. And then this Q over here is this one, where this is the doubling constant. So this Q serves as the counterpart of the dimension for our space. So if we were working on Rn, then well, Q will be N, right? So just bear in mind that this Q comes from our assumption that our space is doubling. Okay, now. Yeah, so assuming that the measure is doubling is like this inequality in terms of the measure of the ball with double the radius, right? All that. And that will imply that something about the if I remember correctly, maybe I will write it completely backwards, but I think it's something like that. This is backwards, maybe something is backwards, but at the end, we get an inequality this way. Like just by assuming that our measure is doubling, we get this. And this is where the coefficient comes from. Okay, now in this work, or actually no, the Euclidean case, the assumption over our coefficient function is non-negative and belonging or being alpha holder continuous for an alpha between 0 and 1. Now, in this work, we're going to assume something similar. We're going to assume that this norm is finite. And I say norm like this because notice that in the denominator of this quotient, we are not working with the distance of our space. We are working with a quasi-distance. And this quasi-distance is given in terms of the measure and, well, the distance, the original distance of our space. Why are we working on this quasi-distance? Well, the short answer is we want it to be as general as possible. And this gives us that. So, for instance, if we're working with a space alphas regular, so mean that we can have a connection between the measure of the ball and radii. If we were assuming this, then the quasi-distance and the original distance in our space are equivalent. And therefore, this assumption, it's basically assuming that A is a Holder continuous function. Okay. Further ahead, I will say whether this quasi-distance plays a significant role. But for now, just bear in mind that we are not working here with the distance. We are working with a quasi-distance. Okay, so finally, the gradient or gradient higher integrability for quasi-minimizers of the double phase problem on metric measure spaces. And for that, we'll first going to define what a local quasi-minimizer is. So a function u in N11 log with h evaluated in its upper gradient locally integrable is going to be called a local quasi-minimizer if there is a constant such that this inequality holds for any test function. Okay? Now, we not only want local results, we want global things. We don't want local. We want to see what happens in our whole domain. So we are gonna need as well the definition of a quasi-minimizer with boundary data. So we start with W, our boundary data, and then we say that a function u in N11 with h evaluated in its upper gradient integrable is a quasi-minimizer with boundary values W if it's different, vanishes outside of omega, and then exists a constant such that this inequality holds for any test function. Now, the main difference between these two definitions that I just gave you are the function spaces. One is local and the other is not. So obviously, a quasi-minimizer with boundary values, it's a local quasi-minimizer. Okay, so again, I'm repeating myself, but it's just to make sure we want higher integrability. We want an improvement on the integrability of the upper gradient for a quasi-minimizer of the double phase. And there's a scheme to prove this. So there are some standard steps. So the first that we are gonna prove is that we have some energy estimates. Okay, then we prove something that we called double-phase Sobolev-Poincaré inequalities. Now, using these two, we are going to obtain a reverse Holder inequality. And this reverse Holder inequality is just an inequality that will hold in any ball in our domain. Now, application of Gering's lemma will give us the desired higher integrability, but it will be again in any of these balls. And again, we want something global. We want something in our whole domain. So after a covering argument, we obtain our result. So that's kind of like this scheme. So let's go through each of one of the steps quickly. Just a very quick note. Every time I say that C, like the constant C, depends on this data, I mean the data that comes from our assumptions of our space. So the doubling constant, the constant of the Poincaré inequality, the dilation factor, the exponents, the constant of the quasi-minimizer definition, the Holder continuity thing, and the norm, Holder norm of our coefficient function. Okay, so first step is to prove energy estimates. So again, we start with local energy estimates. So we start with a local quasi-minimizer, and basically we prove that this inequality holds. And so this inequality is telling us that something in terms of the upper gradient can be bounded with something in terms of the average. Okay, so local quasi-minimizer satisfies this type of inequality. And again, we need the kind of like the global version. So the version for quasi-minimizers with boundary values. So we start with the boundary data, a quasi-minimizer with boundary data W, and then this inequality holds, which again, it's a bound of something in terms of its upper gradient, right? And something that resembles some sort of average, and obviously the boundary data, it's in there. Okay, now double phase Sobolev-Poincaré inequalities. And I need to say something here. Now, let me grab some chalk. When Antonella and I were working with the PQ-Dirichlet problem, which just as a reminder, okay. The PQ-Dirichlet problem we had something like this. We were interested in this integral. And the assumptions that we have over our coefficient functions were that they were away from zero and infinity. So basically, we could kind of forget about them and focus on this type of integral. Basically, we could forget about the coefficient functions and just focus on this type of integral. And then when working on this type of integral, we could divide into cases when the Q term was the dominant one, and what happens when the P term is the dominant one. So our assumption that our space supports a Poincaré inequality is enough. Poincaré inequality has some self-improving properties. So since we could basically divide whether when this integral behaves as a P-Dirichlet integral or as a Q-Dirichlet integral, just using the basic Poincaré inequality was enough. And in metric measure spaces, the basic assumptions in order to us being able to just do first degree calculus are doubling property and a Poincaré inequality, because this combination, with this combination, we will get Vitali covering theorems as well as Lebesgue differentiation theorem. And obviously, Poincaré will imply like Sobolev-Poincaré and so on. But now that we are working with this guy, so GUP plus A of X GUQ D mu, cannot get rid of this guy because this guy can be zero now. So this whole thing just to, and that is why we have a double phase. We call it double phase because it's given in terms of age, Sobolev-Poincaré inequality. So the local version is the following. And this holds for any function in our like N11 log with age evaluating its supergradient locally integrable. Like we don't need to assume that U is a quasi-minimizer. This should hold for anything. But basically, if we have a U there, then there exists some exponents such that this inequality holds. Now, another thing that I want to say. As you can see, well, it does not look that clean, right? This inequality, because we have this term. And one might think, well, why didn't you just absorb this term into the constant, right? We have 1 plus GU LP at a certain ball to Q minus P times something. Okay, so this term, precisely, this is the one that we didn't want to just absorb it with the constant. And this measure of the ball comes from the fact that we are working with a quasi-distance in the like this Holder norm. This from there. So precisely, if we were working with an Alfors regular base, then we would be able to bound this guy in terms of R to an exponent, where this exponent will be bigger than 0. Since without loss of generality, we can assume that this R is small, then we would be able to just bound everything and just absorb very nicely things in the constant. But since we are not assuming that we are working in Alfors regular space, then we just left it there, which it doesn't look clean, but it's okay. Okay, but again, we not only need a local version, we also need a version of double phase of Poincaré inequalities, but in this case, for functions that vanish outside a large set. And why functions that vanish outside a large set? Well, because at some point we're going to work with U, a quasi-minimizer with boundary data. So what does that mean? That U minus W will belong to this space. So it will vanish outside of omega. It will vanish on a large set. And in order to prove the version, we need a measure condition. But the result is basically the same. There exist some exponents such that this inequality holds. And again, we get this like extra term, not extra, but not able to solve it necessarily with the constant. Okay, so now local and global higher integrability results for the upper gradient. And as I mentioned, we use the energy estimates as well as the double phase Sobolev-Poincaré inequality and an application of Gering's lemma, right? So Gering's lemma, what tells us is that if we somehow obtain this reverse Holder inequality for any ball, then we can obtain an improvement in the integrability of our function, but in any ball, okay? So that's precisely what we do. So first, the local higher integrability. So an application of the local estimate plus the local double phase or the interior double phase Poincaré inequality, we obtain the desired reverse Holder inequality. So an application of Gering's lemma gives us the improvement of the integrability in balls, and then a covering argument gives us this one. And as you can see, we introduce some auxiliaries of domains. So we prove the reverse Holder inequality in balls that are compactly contained in omega. And then the covering argument is given in terms of omega prime and omega b prime. And lastly, the global higher integrability. And for this one, we use the global energy estimates plus the double phase Sobolev-Poincaré inequality for functions that vanish on a large set. And we obtain the reverse Holder inequality, and at the end, an application of Gering's lemma gives us as well the high integrability. And I think I'm ahead of time. So what's next? Well, there's plenty still to be done. And actually, Antonella and I just finished another article. And in this one, we hope we were able to prove local boundedness for quasi-minimizers, as well as Harnack inequality and Holder continuity for quasi-minimizers of the double phase and metric measuring spaces. And now the next step, it would be interesting to see what happens up to the boundary. What type of regularity can we get up to the boundary? Can we get some sort of winner criterion, meaning that so the Holder continuity or continuity of our minimizer is determined by the continuity or Holder continuity of the boundary data. That's kind of like the direction we are headed. But I think that's it. So thank you so much.
Thank you, Cintia. Are there any questions from the audience in the internet or the audience here in present? Questions?
So just at the very last slide, were you saying you are hoping that you have proven a local, no, sorry, the what's next, that you can prove local boundedness of the quasi-minimizers. And do you, like, based on what happens on the Euclidean spaces or whatever, do you expect to obtain any regularity at all on the weak derivative, like I mean, can you actually go to the, so what the higher integrability that you obtain is for
the upper gradient? Yeah.
Okay. And do you have any reason to believe, or would you expect at some point to improve that too?
Actually, I don't even know if in the Euclidean case there's something like that. I think it's mainly focused on the minimizer itself, and I'm not sure. I'm not sure about if it belongs to some sort of Holder space or something, but no, like so what we obtained was that the minimizer will belong to a Holder space and 0 something alpha or something solely in terms of the upper gradient.
Thank you.
Yes, sorry. So if in this constant in the Poincaré inequality, you have meaning on the base space?
No, not really. And actually, I think I've been asked something similar, like if we have some sort of how do you say this? Like if it's optimal or something like that. I don't have an answer for that. I don't have like a lot of information regarding the constants, our constants. Mainly what we can say is the dependency. We were very adamant in following what type of dependency these constants have. But beyond that, I don't have further information for the constant itself.
Yeah, thank you very much.
Hi, Cintia. I had a question. So in the case where you take Q equals 0, those are like the minimizers of that. Those are like harmonic functions, P harmonic functions, right?
So Q can, I mean, in our case, Q cannot be 0. Both of the exponents are strictly bigger than 1.
I see.
Yeah. I mean, but. Or you meant A? Yeah.
Well, yes, sorry, A.
Yes, okay, yes. Yeah.
Then in this case, I guess, these are locally Lipschitz, right? In the,
yes, yeah.
So do you expect the same here?
Yeah, like locally Holder continuous, even like the minimizers.
Okay, yeah. But then can you say something more like in the smooth setting for C1, smooth?
Yeah, I mean, at least in metric measure spaces, I'm not sure. I don't know.
Right.
Yeah, and so
But even
yeah.
in the smooth case, is it known? I guess that's my question.
I don't know.
Okay.
So for instance, in metric measure spaces and just restricting ourselves to the P-Dirichlet integral, there has been a lot of work. And actually that's kind of what inspired us to not only think of the P-Dirichlet part, but also like what happens when we add some terms. But yeah, like more regularity or smooth, yeah.
Okay. Thanks.
More questions for Cintia?
Also, just do you know if there is anything done like for other energies with PQ growth or something like this? Does it? I mean, I guess not. If you are.
But no, what do you mean? Like besides like something kind of related to the P-Dirichlet integral, or what do you mean?
Like in metric measure spaces, like these type of results, like the higher integrability or something for minimizers even, and for other energies.
Yeah. So it has been done for example, for the area function, I think, also like just for the P-Dirichlet. I worked even with the total variation flow. So it's basically the limiting case of the P-Dirichlet when P is equal to 1. We did not get high integrability, which is proof certain sufficient conditions for continuity. PQ Dirichlet integral. Now this one, like I think it's headed like to extend results more like functions.
More questions? I have one. I remember that you defined this quasi-distance.
Yeah.
And I was wondering if you have thought about, instead of working with P Laplacians, since you have this quasi-distance and you have all the integrability and all that, is it known? Let me think. Is it possible to define a kind of fractional P Laplacian using that, and to attack fractional problems?
I mean, probably is. Okay, so one thing I did not understand, what was the connection between this quasi-distance and the fractional?
Yeah, because when you use the fractional Laplacian, what you actually have is a double integral of something divided by a distance.
Yeah.
And maybe, I don't know if there is a notion of fractional Laplacian in the metric measure space setting. And I was wondering if maybe this kind of quasi-distance can be used to define a proper P fractional Laplacian.
Yeah. I think at some point, so in order to prove like the Sobolev double phase thing, in the Euclidean case, there are like two types of proof. And precisely one uses this type of fractional thing. And when I was trying to replicate that, I was not able to using the distance, and I left it and I went to another route. Okay. So and I could not find anything related to this type of quotients in metric measure spaces.
And also for higher order operators, it is not known.
I'm not sure. Like probably, no, I am not sure if there's already something done for like fractional Laplacian or metric measure spaces, but now, yeah, maybe using this type of quasi-distance things kind of get.
Yeah, because it looks like this part of the distance that the quasi norm that appears in the fractional setting. It is almost that.
Yeah. I mean, yeah, I'm not sure.
And also a little quick, another quick question. So, and is it known something about higher order operators, for instance, think about the bilaplasian in metric measure spaces? What could be the kind of H2, M2 or something like that? It is not known.
I have to be honest. I don't know, but I am like with the people in Calgary. I'm working with the Monge-Ampere equation, which precisely like it's a mess. I mean, I still need to understand what is it that we are aiming and what is it that we try to do, because precisely we need to introduce something like a second derivative.
Yeah, that's the problem.
So it's still kind of like there's not much, and yeah, it's still on the understanding process.
Okay.
And we have not found lots like anything else. I mean, there's a lot of theory by Chigger about like these derivatives, like just this abstract thing about derivatives. But Chigger, I don't know, the notation is very dense. And yeah, I don't think much has been done.
Okay. Thank you very much. Any more questions for Cintia? If not, we thank again.